So here in this problem we are given that there is an insulated piston cylinder device and it contains saturated liquid vapor mixture with a quality of, or you could say the dryness fraction as 0.1, and its temperature T1 we are given as 100 degrees Celsius, and the volume inside the cylinder it is 0.02 meter cube. And now what we are doing is we are adding ice at minus 18 degrees Celsius, and the final state of the mixture we are given as that T2 it is 100 degrees Celsius, and the value of x2 becomes 0. That means it reaches saturated liquid, and we have to calculate two things. First of all, we have to calculate the amount of mass of ice added to the system, and in the B part we have to calculate the entropy generation. So to solve this problem we'll be requiring some data, that is the value of specific heat of ice, and we know it is 2.11 kilojoule over kg degree Celsius, and the heat of fusion of ice we are given as it is 333.7 kilojoule over kg, and the specific heat of water we know it is 4.18 kilojoule over kg degree Celsius. Now we're going to apply the energy balance equation on the system. So we have energy in. We'll be taking both the ice and the cylinder to be our system. So energy in minus energy out is equals to change in energy of the system. Now energy in, we have the work input, there is no energy out, and it is equals to the change in internal energy of the system, that is delta U. Now here we are going to note that the temperature and the pressure remains constant during this phase change process. Thus we can say the work plus the internal energy will be equals to change in enthalpy. So energy, the energy balance for the system, it will becomes that delta H will be equals to 0. This is delta H of system. So by using this expression we are going to solve this problem. So delta H of system will be equals to the combination of MC, or we can say MH2 minus H1. This is for water. Now delta H of ice then, so plus this will be MC, and now ice will be something like, the initial condition is minus 18 degrees Celsius, so it will first convert into 0 degrees Celsius ice, then 0 degrees Celsius water, and then finally the final temperature which is 100 degrees Celsius as per given in the question. So MC 0 degrees Celsius minus initial temperature is 18 degrees Celsius, so plus 18 degrees Celsius, this is specific heat of ice, plus MC T final minus T initial. So O we can write it as M times HIF, this is the latent heat of fusion, plus MC of water times T final, here is 100 degrees Celsius and initial temperature was 0 degrees Celsius. So and it will be equals to 0. From here we can calculate the mass of ice. This is mass of ice, and this one is also mass of ice. But we don't have the mass of water also. For that we can do one thing. We know that the mass of water will be equals to volume divided by the specific volume at state 1. So we have to find all the properties at state 1. That is the value of H1, H2 also, and then V1 also. So for that we'll be using the table, the steam table as per given in the book. So corresponding to the pressure, temperature we are given T1 is 100 degrees Celsius and X1 we are given as 0.1. So corresponding to these values we can easily calculate VF, HF and SF. So VF we have 0.001043 meter cube over kg, and HF will be 419.17 kilojoule over kg, and SF will be 1.3072. It is kilojoule over kg degree Celsius, and Vg will be 1.6720 meter cube over kg, and HFG will be 2256.4 kilojoule over kg, and SFG from the table it will be 6.0490 kilojoule over kg Kelvin. Now we can easily calculate the value of specific volume at state 1, and its formula will be Vf plus x1 times Vg minus Vf. So Vf we have 0.001043 plus 0.1 Vg minus Vf. So Vg we have 1.6720 minus this one is 0.001043, which will be equals to 0.16814 meter cube over kg. Now next H1. So H1 will be same HF plus x1 times HFG. So HF we have 419.17 kilojoule over kg, plus x1 we have 0.1, HFG we have 2256.4 kilojoule over kg. So we're going to solve this and we'll get the value of H1 as 644.81 kilojoule over kg. Now next I will be calculating the value of S1. So S1 will be equals to SF plus X1 times SFG. So SF we have obtained as 1.3072, X1 we have 0.1, SFG we have 6.0490. So we're going to solve this and we'll get the value of S1 as 1.9119 kilojoule over kg Kelvin. So we have obtained all the desired properties at state 1. Now next I will be calculating the properties at state 2. So the enthalpy at state 2, H2 will be equals to HF corresponding to temperature 100 degrees Celsius. So from the table it will be 419.17 kilojoule over kg, and S2 it will be SF corresponding to the temperature 100 degrees Celsius, and it will be 1.3072 kilojoule over kg Kelvin. Now we have obtained this value of H2 and H1 also, and now we can calculate the value of the mass of water. So the mass of water, we are given as 0.02 meter cube, divided by the specific volume at state 1 we have obtained as 0.16814 meter cube over kg. So after solving this we'll get the value as 0.119 kg. Now we're going to substitute all the value in this formula to calculate the mass of ice. So the mass of water we have obtained as 0.119 kg times H2 we have 419.17 kilojoule over kg minus H1. So H1 we have obtained as 644.81 kilojoule over kg, plus the mass of ice we have to calculate, and the specific heat of ice is 2.11 kilojoule over kg degree Celsius, and this one is 18 degrees Celsius, plus the mass of ice we have to calculate. HIF for ice we are already given in the question as 333.7 kilojoule over kg, plus the mass of ice we have to calculate. Here we have to take the specific heat of water, because in this stage it is converted into water. So specific heat of water is 4.18 kilojoule over kg degree Celsius times 100 minus 0 is 100, and it will be equals to 0. Now here there is only one variable, that is mass of ice, so we can calculate by using our calculator. So mass of ice, from here it comes out to be as 0.034 kg, and if you convert this thing into grams, so we'll get 34 gram of ice. So this is the answer for the A part. Now next we'll be calculating the B part, where we have to calculate the entropy generation during the process. So to calculate the entropy generation, we'll be applying the entropy balance equation on our system, that is the closed system. So we have entropy in minus entropy out plus the entropy generation is equals to change in entropy of the system. So entropy in we have 0, entropy out is also 0. Entropy generation from here comes out to be as change in entropy of the system. That means change in entropy of the steam, the saturated water vapor mixture, plus the entropy change of the ice. So first we'll be calculating this term, entropy change of the steam, and it will be equals to the mass of water times S2 minus S1. So mass of water we have 0.119 kg, S2 we have 1.3072 minus S1 we have obtained from the table as 1.9119 kilojoule over kg Kelvin. So we'll get the value of delta S of steam as nearly negative 0.0719 kilojoule over kg Kelvin. Now next we can calculate the entropy change of the ice, and it will be equal to the summation of delta S of the solid ice, delta S of melting, plus the delta S of liquid, because it is happening in 3 processes. The heat is rejected in 3 processes. So okay, so this one is for ice. Now the mass of the delta S for solid will be mc natural log T melting divided by the initial temperature T1. This one is mhif divided by the temperature of melting, the melting temperature, times mc natural log T2 divided by T1 for liquid this time. So you can plug all these value here. We can take the mass of ice outside the common also, which will be 0.034 kg. Okay, see the specific heat for ice we have 2.11 kilojoule over kg Kelvin. The melting temperature we have 273.15 Kelvin divided by the initial temperature T1 we have 255.15 Kelvin, plus the M we have already taken out. So HIF we have given in the equation as it is 333.7 divided by the temperature of melting we have 273.15, plus this one is 4.18 natural log T2 we have 373.15 Kelvin, and basically the temperature T1 at state 1, this is the T1, this is T2, so T1 we have 273.15, and mass we have already taken out common. So we're going to solve this and we'll get the value as 0.0907 kilojoule over Kelvin. Now we can do one thing, we can add both these numbers to calculate the entropy generation. So entropy generation, it will be this one is negative 0. That is the delta S for steam, it is negative 0.0719 kilojoule over kg Kelvin, and this one is 0.0907 kilojoule over kg Kelvin. Now adding both the numbers we'll get 0.0188 kilojoule over Kelvin. So this is the final answer for the B part. I hope you got the problem. Thank you.